Now to some more pure mathematics. Some basic questions that occur to anyone dealing with sequences might be, how can we tell whether a given sequence remains bounded or grows larger and larger without bound? Some clarification is needed here. A sequence AN is bounded above if there's a number capital K such that AN is less than capital K for all n. For example, the sequence 1 over n is bounded above by 1. The sequence minus n is also bounded above, since it starts at minus 1 and moves left. It often helps to plot a sequence on the number line to get a feeling for what it is doing. From the picture, we can see that the first sequence is always moving to the left, approaching 0, while the second is also always moving left, but not approaching any number. Dually, a sequence Bn is bounded below if there's a number k such that k lies to the left of the elements of the sequence for all n. The sequence 1 over n is bounded below by 0, since the terms are all positive. The sequence minus n is not bounded below. We say that a sequence is bounded if it is bounded above and below. If a sequence remains bounded, does it get closer and closer to some fixed number, is another question we might ask. We could also ask, does it oscillate, getting closer and closer to several different numbers in a regular way? And finally, we might have a situation where we could ask, does it behave chaotically, in the sense that we cannot predict what it will do? Well, to determine that a sequence is bounded is easy if the sequence is given by an explicit formula. For example, the sequence an equals the sine of the natural number n is certainly bounded, since the sine function takes on values between minus 1 and plus 1. The only difficulty is in the formula. We may have to sweat a bit to get bounds or to show the sequence is unbounded. For example, consider the sequence Bn equals n to the 100th power divided by 2 to the nth power. This sequence is indeed bounded, but to prove that requires a deeper understanding of the growth rates of the functions x to the 100 and 2 to the x. And the conclusion is that exponentials rule. For recursively defined sequences, proving or disproving boundedness can be a real challenge. Consider the sequence defined by a1 equals 1. an plus 1 is twice an minus 3. Then the first few terms are 1, minus 5, minus 13, minus 29. It certainly looks like the sequence is unbounded below. And it is easy enough to prove. We see that a2 is minus 1 less than 0. Then a3 is twice minus 1 minus 3. And we throw away the minus 3 so that a3 is less than twice minus 1, which is minus 2. Then we write a4, which is twice a3 minus 3. a3 in turn is less than minus 2. So we put in minus 2 for a3, creating a larger number, twice minus 2 minus 3, and that's minus 4 minus 3. And we throw away the minus 3 again, and we say that a4 is less than minus 4. We just keep throwing away that term minus 3 because it clutters up the argument. Now with the help of induction, we can prove that a of 2 plus j is less than minus the number 2 to the j. Try a few more terms to convince yourself. So the terms are unbounded below. But what an increase in abstraction when we started addressing these questions. For now in this lecture, we will focus on getting a feel for things. The hard stuff will come in a later lecture. Now if a sequence is bounded, does it converge? That is, get closer and closer to some given number? The answer is not necessarily. Here's an easy counterexample. The sequence minus 1 to the nth oscillates between two values, minus 1 and plus 1, depending on whether n is odd or even. And if we wanted to get closer and closer, rather than land on the values, we can modify the sequence. Consider the new sequence, minus 1 to the nth plus 1 over n, which oscillates between sort of minus 1 and sort of plus 1 and gets closer and closer to those 2 points. For chaotic behavior, which we avoid defining by just giving an example, consider the numbers sine of n. This is a bounded sequence, but does not get close to any set of numbers. In fact, given any real number x between minus 1 and 1, this sequence has a subset of infinitely many terms, which we call a subsequence, which approaches that number. In short, the values are all over the map and stay all over the map within the interval minus 1, 1. Finally, we should present some positive results on convergence to offset the gloom, or maybe sense of excitement, created by the previous example. First of all, we say a sequence Cn is monotone increasing if Cn plus 1 is bigger than or equal to Cn for all n. It is strictly increasing if the inequality is strict. Visually, it means that the sequence is always moving to the right. For monotone sequences, we allow the sequence to sit on one spot for a while or forever. For strictly increasing sequences, the sequence must move to the right all the time. Monotone decreasing and strictly decreasing sequences have a dual definition. Monotone decreasing means that Cn plus 1 is less than or equal to Cn. Strictly decreasing means that Cn plus 1 is strictly less than Cn, again for all n. For example, the sequence 1 over n is strictly decreasing since 1 over n plus 1 is less than 1 over n. The sequence sin n pi is both monotone decreasing and monotone increasing because it really just sits on the value 0. If you don't see this, plot a few points on the real number line. Theorem: if the sequence an is monotone increasing and bounded above, then that sequence converges to a limit. If the sequence is monotone decreasing and bounded below, then it converges to a limit. The results are still true if monotone is replaced by strictly. At this point, we need to carefully define what we mean by convergence to a limit. Here is the somewhat intimidating definition. The sequence an converges to the number L, called the limit of the sequence, if, given any number epsilon, there is a natural number n, depending on epsilon, such that if the natural number n is greater than n sub epsilon, then the difference between an and L in absolute value is less than epsilon. Well, I told you it was a bit intimidating, but here is what it says in plain English. The terms in the sequence will eventually get close and stay close to L. You tell me how close you want to be. Give me a positive epsilon, and I will tell you how far you have to go in the series before the terms all stay within epsilon of L. To reinforce the plain English, here is a picture. We won't work with this definition, nor will we prove the theorem above at this point, but we wanted to lay out some of the powerful theory at this early stage. One excellent example of the power of this theorem is the following. The sequence 1 plus 1 over n, all raised to the nth power, is bounded and strictly increasing. This is not too difficult to show. Therefore, our theorem implies that it will converge to a limit, and in fact that limit is the number e. We're not going to prove this until later in the course, but I hope it piques your interest in sequences.